Yeah, we're solving more logarithmic equations today. Yesterday we were doing mostly exponential stuff. Today we're bringing in the log. It's the same stuff, man. Come on. To solve a logarithmic equation, use this property for logarithms with the same base. Okay, if you look, it kind of just makes sense. This is log sub 3, 5x minus 1 equals log sub 3, x plus 7. They both have the log sub 3, right? So really all we have to do is set these parts equal to each other. 5x minus 1 equals x plus 7 because it needs to be balanced, it needs to be the same. 5x minus 1 equals x plus 7. And this is a pretty darn easy equation to solve. Subtract an x from both sides, 4x minus 1 equals 7. We'll add 1 to both sides, 4x equals 8. And then we'll divide by the 4, which would give us x equals 2. Now, as it always is, it's usually a great idea to check your answers because eventually we're going to end up with some extraneous solutions today where when you sub them back in, they don't work. So if we sub this back in, 5 times 2 is 10, minus 1 is 9. So this would be log sub 3, 9. Over here, 2 plus 7 is 9. So log sub 3, 9 equals log sub 3, 9. Great, it's the same thing on both sides. We're good. All right. Now here, we can set up equations with like old stuff we know here. So don't write what I'm about to write if you're writing at home, because we're going to actually write it a different way. But think of what this means. This is saying 3 to the x, or to the second power, is equal to this x minus 5. And that's actually fine if you do want to solve it that way. But the official way that people much smarter than me would set it up is they would say to exponentiate each side. Remember, if you do something to one side of the equation, as long as you do it to the other side, you're all good. So we're going to go basically to that property where it was like 31 to the log sub 31 50th power. And the 31 and the log sub 31 are inverse, so they cancel out. So we'd be left with 50. That's the what am I looking for? That's the property that we're going to use here. So here we have log sub 3 x minus 5 equals 2. We're just going to put a 3 as a base on both sides. So the 3 to the log sub 3 power all cancels out, so we're just left with x minus 5 equals 3 to the second power is just 9. Now, you might remember that's the exact same equation we had before. We had 3 to the second equals x minus 5, and 3 to the second is 9. So this is all good. We'll add the 5 to both sides, and we will get x equals 14. If you substitute that into the original equation, log sub 3, 14 minus 5 is 9, and 3 to the second power is 9. So it all checks out. So if we do that here, I see it's log sub 5. So we're just going to bring in a base of 5 on both sides. And the 5 to the log sub 5 power all cancels out. So we are just left with 3x plus 1 over here. And then 5 to the second power is 25 over here. I'm going to move right to the middle. And we will subtract the 1, which would give us 3x equals 24. We'll divide by the 3, which gives us x equals 8. If you substitute that back into the original equation, log sub 5, 3 times 8 is 24, plus 1 is 25. And this is true because 5 to the second power equals 25. I believe we have 2 more down here, and we're going to have to drop in one of the old condensing properties before we're able to solve this. So remember, you can only condense them if they are the same base, which all of the problems we're going to have are. Here, log 45x minus log 3. Remember, when there's subtraction between them and you're condensing, you divide that. So we're going to be doing 45x divided by 3. And again, from here, you can set up your equation. There's an invisible 10 down here. So you can say 10 to the first power equals this, right? We're not going to do it that way, but you can. I gotta sneeze here in a minute. I'm gonna simplify this 45x divided by 3. Oh, goodness. Now, the 10 isn't written usually. I'm just gonna write it. It's okay if you don't. 45x divided by 3 is 15x equals 1. And then we're going to drop in the base. Drop that base. The base here is 10. Again, it wouldn't ordinarily be written, so you just have to remember that. So we're going to drop a 10 in on both sides. These will all cancel. So we have 15x equals 10 to the first power is 10. Now when we divide by 15, we're going to get a fraction here. 10/15 reduces to 2/3. So you get x equals 2/3. Now, if you were to substitute that back in to the original, 45 times 2/3 is 30. And then if you bring this together with division, 30 divided by 3 is 10. And log 10 does equal 1 because 10 to the first power equals 10. Great. Now here we have subtraction again, so we're going to bring it together with division. Let me move over here. Log sub 4 100 over x plus 1 equals 1. Bring in that base of 4. That will cancel out all this, so we have 100 over x plus 1 equals 4 to the first power is 4. We're going to get rid of the x plus 1 by multiplying both sides by x plus 1. Which is going to turn into like a distribution problem over here. This side just cancels, so we have 100 equals, and then 4x plus 4. We'll subtract our 4, 96 equals 4x. And then when you divide by 4, you end up with 24 for x. If you substitute that back into the original equation, we have log sub 4 100 minus log sub 4, 24 plus 1 is 25. And then you divide those, so you end up with log sub 4 equals 1, and 4 to the first power equals 4. Great, it all works out. Here is the ones where we're going to have to actually worry about some extraneous solutions when we substitute it back. So if we were to bring this together, there's addition between them, so that means we're going to multiply this. So if we multiply 5x times x, we get 5x squared. 5x times -1 is -5x. And if we exponentiate here, we drop in a base 10 because there's an invisible 10 there. These cancel, so we're left with 5x squared minus 5x equals 10 squared is 100. Now when you're factoring, you have to have it equal to 0 to do that. So when you're factoring to solve, so we would have to subtract the 100. Greatest common factor is 5, which will leave us with x squared minus x minus 20. The factors of 20 are 1 apart, be 5 and 4. X minus 5, x plus 4, which will give us two answers here. X equals 5, and x equals -4. Now, it's okay if we end up with two answers, but you do want to check them because oftentimes in these problems, one of them won't work. So if we were to substitute those into the original, if I substitute in 5, 5 times 5 is 25, and over here, 5 minus 1 is 4. So we bring this together and say log 100 equals 2. And that's true. 10 to the second power equals 100. So that one works. Now, when we bring in -4, 5 times -4 is -20. And here's already the problem. But I'll write the rest. and negative 4 minus 1 is negative 5. So if you do multiply these, negative 20 times negative 5 is positive 100. But you can't simplify these because 10 to the something power can never come out to equal negative 20, right? Because even if you had a negative exponent on the 10, it would come out as a fraction, right? So you can't go from a positive number with an exponent and make it negative. So this part, if you put it in your calculator, log sum 10, negative 20, it's going to tell you it's undefined. So you can never have a positive base with a negative number here. So that makes this an extraneous solution. Now that's not to say that every time you end up with a negative answer, that it won't work out. So let's say an instance of that would be like if you had log negative 4x. Because then if your x was negative, negative 4 times negative whatever would come out positive, and that would be fine. Most of the time it is the negative answer that's extraneous, but not 100% of the time. So you do have to be careful. All right, again, we're bringing it together with multiplication. Logs of 12. X times x would be x squared. X times 1 would be x. If we exponentiate, drop a 12 in on both sides, because I'll cancel. X squared plus x equals 12 in the first. Subtract that 12 over x squared plus x minus 12 equals 0. What factors of 12 are 1 apart? 4 and 3. X plus 4, x minus 3. And our two answers would be negative 4 and positive 3. Maybe they'll both work. Probably not. If we were to put in negative 4, I already see a problem. Right here. 12 to the something power can never equal negative 4. So right there, negative 4 is an extraneous solution. We'll try it with 3. If 3 doesn't work, then there would be no solutions on this. So let's see, log 12 sub 3. Okay, it's positive and positive, that's good. Plus log sub 12, 3 plus 1 is 4. We bring this together with multiplication. We have log sub 12, 12 equals 1. 12 to the first power equals 12. So 3 is our only solution on that one. I think we got one more problem. Little word problem. Ooh. The moment magnitude M of an earthquake that releases energy E in ergs can be modeled by this equation. On May 22nd, 1960, a powerful earthquake took place in Chile. It had a moment magnitude of 9.5. How much energy did this earthquake release? So we're subbing this in for M right here. We have 9.5 equals 0.291 ln plus 117. Now we've been dealing with logarithms. This ln is a natural logarithm. It has the same properties as logarithms, but we're really going to talk about it more in chapter 4.6, which talks about the natural base e. So you know how with logarithms, it's like a base 10 if it's not written? With natural logs like this, it's an invisible e. And e is just like, it's almost like pi. It's just an irrational number. I don't know how they calculated it, but it's like 2.17 or 2.71 or something like that. So that's what we're going to use when we see ln to cancel it out. We're going to use e. So let's hop over here. First thing we have to do is get rid of that 117. So we'll subtract the 117. Let's see, 9.5 minus 117. Oh, can we do that? Oh, I put in too many decimal spots. Decimal spots. Negative 107.5 QSFM equals 0.291 ln e. It's being multiplied, so we'll divide by the 0.291. divided by 0.291. Negative 369.416, let's call it. That is ln of e. Now, again, with the natural logarithm, it's like they have an invisible sub e over here. Now we have to cancel out that sub e. So we're going to drop it in, just like we did with the regular numbers. We're going to bring in a new base of e to both sides. So the e to the natural logarithm sub e, this will all cancel out. So all we're left with is the capital E. It's kind of confusing in this formula because there's lots of e's and they're different things. So this lowercase e is different than this uppercase e because the uppercase e is what they say is we're measuring in ergs. So, all right, so we have to do e to the negative 369.416 power. So a lot of times on your calculator, if you go towards the logarithm, it'll say like, I'll see if you can see on mine. So I went to my logarithm menu. You probably can't see. And then to the right, see how it says ln? So if I go to the right, oh, shoot. Oh, shoot. Come on. Oh, okay. Then my second option there is e to the whatever power. Wow, that's really not working there. All right. So e to the negative 369.416 power, 0. That doesn't seem right. Maybe I goofed something. Oh boy. Oh my gosh, it's 1.17, Mr. Plant, not 117. Well, I guess that's good that I realized my answer didn't make any sense. This is probably a riveting video. Alright, 9.5 minus 1.17 is 8.33. Okay, here we go. Now we're on. We still have to divide by the 0.291. 28.625. 28.625 equals the natural logarithm of e. Remember to cancel out that ln. We're going to drop in a base of e. Because e to the ln sub e, right? Invisible sub e, this all cancels out. So we're left with the capital E, which is the ergs, equals e to the 28.625 power. Oh wow, they're giving it to me in scientific notation. 2.702 times 10 to the 12th power. Now if we were to write that, and of course that's a rounded decimal right there, but if we were to write that in standard notation, that means we're moving the decimal 12 places to the right. So if I moved it 3 times, it'd be 2702. I have to put 9 more zeros behind that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is ergs. Erg. Erg. Hey, we're done. We did it. We did it. Oh, yeah.